Okay. Okay, now it's been recorded. Cool. All right. So I study at the moment problems on one-counter nets and vector addition systems with states. I'll refer to one-counter nets as OCNs and vector addition system with states as VAS. And sort of on the side, semi-linear sets pop up every now and again, kind of inspired from Dimitri's sort of recent work or kind of ongoing work on them. I'll also kind of just very briefly cover a few definitions of some complexity classes that seem to pop up a lot in these subject matters, namely the first and second level of the polynomial hierarchy. I'll kind of define them in the form of, here's their canonical complete problem, and don't worry about the kind of semantics of what they mean in terms of Turing machines. And another one would be the complexity class NL. Some of this might be really boring to some of you, but there's quite a wide background, I think, here, so I just thought I might as well. And then I'll move on to decision problems, that sort of arbitrary decision problems that you can apply to most, if not all, automata that I may or may not care about. Stuff like membership, compressed membership, universality, and then kind of reachability and coverability, though these are more specific to VAS type genes. And then the best bit, hopefully I don't ramble too much and I get to the end, I'll talk about open complexity gaps of problems that are kind of interest, and maybe some new variations of some pre-existing automata. I say new because I don't know if they've been discovered before, but I'm certainly thinking about them for the first time, and hopefully they help me attack some of these problems. And just as a side comment, if you know anything obvious about what I present that I've clearly not seen, just tell me afterwards. I'm really keen to kind of gain as much knowledge as possible at the moment. Okay, I guess let's go. So presentation slide 2. I'm going to define if it would load. This is a bit unfortunate, isn't it? There we go. Right. So I'll define the 3 types of kind of objects, if you will, that I like. So semi-linear sets, one-counter nets, and vector addition system with states. There's a lot going on, so I'll talk you through and then I'll pen up an example, so hopefully it's kind of clear. A semi-linear set is a finite union, so union here, I equals 1 to n, of these guys, and L, Bi, Pi represent linear sets. I'll kind of give an example of a linear set in a moment. We say that Bi is the base vector, and we say Pi is a kind of set of a certain number here, Ki vectors. We call those periods. The idea is that any element belonging to S is a sum of a base vector and any number of any of the period vectors. And just to kind of give an example of a linear set, and then you can kind of augment the, if you will, the union in your head. We'll take like the chicken nugget problem, right? So in this case, we have B equals 0 and P, this is just the sort of one-dimensional case. You kind of upscale this if you like. So imagine you're buying chicken nuggets in multiples that McDonald's sell them in, right? Which is 4, 6, 9, and 20, the last time I knew or checked. The idea is that the linear set LBP is kind of, in this case, all of the chicken nugget combinations you can buy, right? So you can buy something, you can buy a group of 4, you could buy a group of 6, you can buy a group of 8, right? Because you can buy 2 groups of 4, you can buy a 9 outright, you can buy a 10 by buying a 4 and a 6. You can't make 11, you can make 12 in a number of ways. You get the idea. And this is kind of the chicken nugget problem. There's this sort of famous problem associated with it called the Frobenius coin problem, in which you're given coin denominations kind of like this, and you're asked what is the largest amount of money that change cannot be made for. In the chicken nugget world, this would be, what's the largest number of chicken nuggets that McDonald's can't serve you in a normal kind of quantity. I don't know the exact numbers here. I think it's something like 23. I don't think it's that important, but that's kind of what a linear set looks like. And now if you just take a linear set, union it with n other linear sets, you get something that's semi-linear. There's kind of, there are drawings that represent what these look like and feel like, but it would take too long, so I kind of skipped over it. I hope this makes sense. And the kind of base vector would be, if in the chicken nugget world, maybe if you were given 10 chicken nuggets for free and someone made you eat them, then you would say the only combinations you can get are 10 plus all of these. So 14, 16, 18, 19, 20, 22, etc. Just as an example. Okay, okay, let's move on to counternets. One counternet, I've kind of written out the formal tuple of stuff that makes up a counternet, right? We have sigma, the input alphabet. So think of like DFAs and NFAs here, because they're kind of similar. Q as the set of states. Say S naught or Q naught, whatever you prefer, as your starting state. You have a transition function, which I'll talk about in a moment, and then you have a set of final states. The transition function takes two states, so you have two states, the starting and ending state of kind of the direction, right? So if I imagine drawing this out, let's suppose the second one is final. This guy's called P, this guy's called Q, and you equip it with some letter and a natural number. So let's suppose it reads an A. I'll write that on the top half of the transition, and on the bottom half, it kind of updates the one counter with this value here. So I'll call this value the counter update. So imagine kind of coming into state P, you had kind of this word, and you say maybe you would have read the first letter. You could take this transition reading the second letter, and if your counter, let's call it C, was equal to 5, after taking this transition, it would now be updated to 28. I hope this makes sense. And then you can kind of imagine like more transitions coming off. There's a big condition that is not written down here, which is the kind of the counter non-negativity, counter non-neg. If your counter value were to ever dip below 0, so -1, -2, etc., you would kind of crash, just immediately reject, as if you had kind of entered some dead state. Kind of an example here would be if you had a -50 on a B, you couldn't take this transition from state Q out because, okay, sure, you can read the B in your input, but you can't afford the -50 counter value hit because this would send you to some -22. That's kind of illegal in this model. So acceptance is kind of like what you expect in DFAs and NFAs, but there's obviously a bit more going on, right? Because you have counter values that restrict certain edges and paths because they might kind of make you go into like an illegal negative counter. And one last note on encodings, I'll kind of talk about this briefly, but there are kind of combinations of one counter nets that people like to study. You have unary input alphabet ones. So that's, I'll call that unary in alph. That's sigma is just a single letter, right? Just say A in this case. You can have binary ones, input alphabets, in which you kind of have more than just A, say A, B, kind of like this example here. I will generally be focusing on the unary case. I'll talk a bit later maybe why. The binary ones are kind of more complex, but for now, the unary ones seem interesting. And you can also have different encodings for the updates. So if you say the updates are encoded in unary, I'll call it unary update. I'll just move slightly to the side because I've not given myself much space. If updates are any one of these three, so you're allowed to either take one, not add, or take anything, or just add one. And then a binary update is you can take or remove anything. So this is kind of like plus minus n, any natural number. And the kind of idea is that we imagine keeping the encoding small by writing these numbers in binary, whereas for the unary case, we don't really care. We just can represent it with a bit or two. I hope this makes sense. In the example, I've drawn a binary, or part of a binary one counter net, because these updates are clearly not plus minus 1 or 0. They're something a lot bigger. Therefore, we have binary case. And similarly, I will be caring about the binary updates case more, and I'll kind of be careful later why. So think for now, unary alphabet, so just A's, and binary counter updates, so plus minus whatever we want. And the catch, you can also have non-determinism. So rather than reading an A, you can have an epsilon transition. That can still have an associated counter update. It doesn't have to be a +0, say. It can have any update you like, but you can afford not to read the input for a certain transition. Okay, cool. I think that's covered one counternets. Let's move on to vector addition systems with states. They're kind of seemingly more simple than one counternets because we don't have this nonsense to do language and letters read, though there's kind of a lot to them. Here, V, the vector addition system with states, has a set of states and a set of transitions. That's all we really care about. There's kind of the idea of acceptance is kind of not the same here. We study problems on the VAS rather than languages VAS accept. And transitions look like this thing here. So they take a state and another state. So in this example, P and Q, let's write them out again, P and Q, kind of like before. And you attach a vector along it. In this case, this vector kind of has an undefined length. I'll just give an example of a 2 VAS. So you say a k-dimensional VAS is a k-VAS. In this case, I'll have dimension 2. So this will be a 2 VAS. And what that means is we have sort of 2 counters, or in the general case, k counters. And you can update them with whatever you like. They're kind of component-wise. This is the update to the first counter, and this is the update to the second counter. And that's the kind of cost between moving along them. Again, we'll have the non-negativity constraint on counters, sorry. So if any of the k counters dip below 0, just like in one counternets, we will kind of crash. We won't let that run continue any further. And similarly, we can have encodings, but here we only have 2 choices, right? In this, we kind of had 4, right? We could have any combination of unary updates and unary input alphabets, or binary updates and binary input alphabets. You can kind of imagine picking the 4 combinations out of the 2. In vector addition systems, there's only 2. You have unary and binary, and they only refer to the updates on the counters. So again, unary is the same. In this case, this first counter is receiving a unary update. That would be +1, +0, or -1, and binary updates plus, minus, whatever you like. And again, we'll come back to kind of, obviously, unary VAS seem a bit more simple, right? But maybe not. We'll come back to it later. Hopefully, this is good so far. So let's move on to the next slide. So that's an introduction to the kind of machines and semilinear sets. Here's number 3. I'm going to kind of now define a bit more carefully the polynomial, well, not really carefully if I'm being honest, the polynomial hierarchy at level 1 and 2, and then kind of mention what NL, non-deterministic log space, looks like, and just touch on a decision problem just to get in the flavor of what I like to study. So let's go first with the polynomial hierarchy. This sort of left bracket represents level 1, which is kind of NP or co-NP. The canonical problem hopefully is familiar to everyone, right? Which is just SAT. You take some sort of Boolean formula, phi in variables x1 to xn, and you'll ask the question, is there assignment? So alpha1 to x1, alpha2 to x2, etc., alpha n to xn, such that phi of this kind of example is true. This guy is kind of the cornerstone of an NP complete problem. I'll call it level 1 complete for this example, because NP and co-NP, you could swap this out. You could do something about, I think it's instead of having like conjunctive normal form, if you have disjunctive normal form and you ask rather than kind of does there exist, you say is there for all, but you get the point. This is an NP complete problem. And then I'm going to go up a layer to, I've called it SAT squared. I don't think that's a very good name for it. But it's sat at the next level of the hierarchy. We just slap another quantifier in front, but with an alternation. So similarly, we inputted a Boolean formula in normal form, but here we have an extra variable, so x1 to xn and y. And the question is, for all beta, which will be assigned to y, and then does there exist an alpha1 to alpha n assigned to x1 to xn, such that this thing's true? We kind of have this quantifier alternation at the front. We say that this then gets us to the second layer of the polynomial hierarchy. You can kind of imagine this as being a lot harder than SAT, right? Because not only are you having to solve an instance of SAT, you're having to do it kind of arbitrarily many times for however many betas you might have to alternate over or kind of check over. We say this is complete for level 2. you can then kind of append more quantifiers to go further up the layers. I hope this is fairly clear. Level 2 kind of can be described by these complexity classes. So this is NP to the co-NP, and this other one's co-NP to the NP. This notation is, I'm going to very informally mention, is your problem can be solved in NP time with access to a co-NP oracle. And then alternatively, the same thing the way around, co-NP to the NP is a co-NP problem with access to an NP oracle. This complexity class will be of interest. I'll come back to kind of problems that belong and maybe complete to this later. I'm not sure exactly if the phrasing of what I've called SAT squared is correct, but it has the flavor of what I want to kind of be thought of as level 2 complete. It's an alternation ahead of SAT. And then if you've heard of QSAT, which is kind of fully quantified SAT, that's kind of complete for an arbitrary layer of the polynomial hierarchy, or even if you have a kind of non-determined number of quantifications, that would be complete for like P space, which is kind of the ceiling of the polynomial hierarchy, if you will. I know that seems a bit informal, but I hope that makes sense. And then log space, let's quickly do log space. So non-deterministic log space is kind of what it says in the tin, but there's a little bit of detail. You're allowed non-determinism and you have log space. So you have O log n memory, fine. You have a bonus read-only input tape, because if you're given an input which is kind of linear in length, right, then you've got to be able to read the input to solve a problem, at least normally. So we have this extra read. You can't obviously write bits and bytes to it. That would be like illegal. You would end up having more than log n memory in that sense. So we only have log n memory to play with, but we have an extra sort of linear amount of read-only memory for the input. And then I'm just going to write like non-determinism, so non-det is okay. We'll give it a smiley face. And for this, the canonical problem, at least that I like to think of, is graph reachability. So input a graph directed. You have a start state and an end state, and just a simple question: can you get from the start state to the end state? The idea is you non-deterministically guess between each of the transitions, and you don't need to remember your past if you can non-deterministically guess very well. So you just remember the state you're at, and therefore look at the transitions that I have available to you, move on, repeat. So only very basic problems belong in NL, and maybe you'll see later some nice NL problems, and you can see why they're sort of easy. I like to think of NL as a sort of sign that something's easy. It might not be easy to show something's in NL, but they sort of show you the problem is somehow simple. All right, and now coming on to a decision problem of interest, or maybe not of interest, but it's a toy one. Emptiness. It's kind of a classic problem, if you will. You input some language or a set or an automata. So in the example here, we take a semi-linear set as input. So that would be something of the form S in union. So you give each of the linear sets, right? So you give these integers and you give these sets of integers, you should write them down. And you ask the question, is this thing, so in this case, is S equal to the empty set? And it seems easier for semi-linear sets, right? Because any linear set with any values, even if you have an empty period vector set, you still get for free that BI belongs to this this set here, LBI empty. So this thing is clearly not equal to the empty set. So maybe for semi-linear sets, this problem's a bit boring. But for one counter-nest, it already seems a little bit more interesting, although it is pretty simple. So I'll kind of write easy here. But for one counter-nest, it's sort of more interesting. You may have a path to an accepting state. And that means that there'll be some word that gets you to the final state. But it might not be kind of legal, right? Because you may have like a +5 and then a -10 and then a +2. You kind of get hit by, at this point, the non-negativity constraint on the counter, right? If this was the only route to the accepting state, that is. because +5 minus 10 gets you to -5, right? And then you suddenly have like an illegal counter value. So maybe emptiness for one counternet is a little bit more easy, a little bit more difficult, sorry. Probably not, but just as a sort of an example, you can imagine that kind of the thought process that might need to go into this. You kind of have to care about every possible component of the one counternet. Okay, 20 minutes in. Any questions so far with definitions and examples? Because I think this is like the background and the rest of it should follow from here. Sorry if this is like super.
So just to make sure I get semi-linear sets properly, it's basically like so like it's an offset base plus a span, but you can't do negative coefficients for your span vectors. Yeah, basically.
Yeah. So yeah, I didn't make that super clear. You can only add elements from PI, and PI have elements from the natural numbers. So everything in S will be a natural number in that the number of, like, if you think back to the chicken nuggets problem, you can't have negative quantity of chicken nuggets and you can't have negative multiples of chicken nuggets. They must be both positive in both senses. So yeah, cool.
Yep, I get you. Cheers.
You're welcome. Right. Number 4. So I think I'm on number 4. Yes. Okay, cool. So now I'm going to come over to VAS. This might seem a bit like there's kind of a lot going on. Hopefully I'll talk through it nicely. This is kind of where I hope I did this correctly. I don't want to kind of offend anyone who likes VAS as well. So I'll kind of notate here. So I'm looking at the center of this blue weird, not circular, not square box. Define a configuration, right? So I will take a state and a vector. So remember that vectors are like k-dimensional in n to the k. I like this notation. It makes Q look like a function, but it's not. It's just like a clean way of writing down a configuration. And a configuration is simply Q is the state you're at, and the vector V represents the kind of component-wise values that belong to each of the counters. I'll use this notation. You can probably see it littered around the page. I'll be probably using this more than once. So that's what a configuration looks like. Okay, so now let's define some like nice problems on VAS. Coverability and reachability, they're very similar, but with a subtle and very important difference. Hopefully I'll make it clear. Let's start on the right-hand side with reachability, because it's slightly simpler, though not easier. You take as input a k-VAS V, so you know k is a kind of fixed constant. 2 states, P, Q, and 2 vectors, V0 and V. This kind of weird vector hat might not be the clearest or most prettily drawn here, but hopefully it's not too bad. Alternatively, you can think of this input as 2 configurations, P, V0, and Q with V. But just to kind of expand it out and write it in full, if you will, I've taken 2 states and 2 vectors. And then the question you ask is there some run, call it R, in the vector addition system with states V that takes you from your initial configuration along this run? I know this notation is kind of almost disgusting and informal. It's like, oh, I run along via R to state Q with counter values V. And that's kind of reachability in a nutshell. I don't know if I like the word reachability here, but hopefully you associate this problem. And note, this is kind of an exact hit. Like, you need counter value 1 to kind of have exactly the right value from the first component of vector V. Same with counter value 2. You can't like miss one of them. You have to have all of them kind of at the correct counter value. Seems kind of tricky, right? And there's like a little complexity table. So we have dimension down the length, and then we have encodings, right? So from earlier, we allowed unary encodings that are transitions or updates to each of the counter of the form +/-1 and 0, and then binary ones, which are kind of anything we like. And dimension represents the number of counters, if you will, or the dimension of the vectors, whichever way I like to think of it. So I'll just cover the kind of complexities, and you'll see how bonkers these get. So I think these are correct. I did a check yesterday, but they're littered around various papers. If I write this means complexity class NL complete dash C. I don't want to write the whole of complete, it'll get messy. So unary dimension 1 reachability, NL complete, turns out the same holds for dimension 2. In the binary setting, if we immediately go up, we get NP completeness, NP-C, and immediately, even with just dimension 2, we get p-space completeness just immediately. And so the dimension 2 binary, right, that's just 2 counter values along each transition with updates written however you like. You take in sort of 2 configurations, that's already p-space complete. You can imagine showing NP hardness quite easily by encoding subset sum or partition on the edges of these and have states represent kind of decisions of whether you include an element from your subset or not. But p-space completeness maybe to me is slightly surprising, but it shows how hard this problem is. And we're only in dimension 2, right? Hence why I drew this blue line. It's kind of like the scary zone. Not much is known, to be honest. It's kind of bonkers down here. Obviously, we have p-space hardness in the binary setting from dimension 3 downwards. And there is an upper bound, so it's decidable, which is good. But this upper bound is significantly larger than non-elementary. And non-elementary, just for definition, is tower of exponentials. So if it's significantly ahead of non-elementary, this problem's like really tough. So that kind of exists. There's a bit more of a formal bound. Upper bound is Ackermann. Oh, okay. It must have been okay. I must be slightly mistaken then. But thank you. Unless that's the coverability. But I trust Alex here. Alex is my vast wizard, I think. Okay. I'll read that paper. Thank you. And then in the unary case, we get NL hardness. And curiously, I'll just mention it. At dimension 7, we get NP hardness. Yeah, it's kind of crazy. Turns out you can trade 3 counters for a unary counters for a binary one. And so then you get 2 binary counters and a unary. You can get NP hardness from this. I don't fully understand the proof. It's kind of crazy. But the upper bound here is also pretty tough. I think it might be the same as the binary upper bound. But the point is they get hard and there are lots of open complexity gaps for every single dimension 3 onwards. So that's reachability. Now to define coverability, and you'll see why they're similar, hopefully. So, coverability, same input, k-vas, 2 states, 2 vectors. Looking good. The question is almost identical. So does there exist some run R in the VAS, so just as before, that takes you from the starting state with initial counter values in V, 0, to the final state, or that should be a Q, there's a nice little typo there. Let me correct that. With values V prime, sort of note that prime, that's important. But the condition on V prime is that V prime is at least V component wise. So each of the components in the vector is greater than or equal to each of the components in the original vector. So coverability is kind of like, can I reach a slightly bigger configuration? And by bigger, we mean the counter values have bigger values in them. This is immediately slightly harder, right? Because this is kind of like the equality case in reachability, and this is the kind of inequality case. So if you could do reachability, obviously you can do coverability because you can kind of unrelax your constraint. But yeah, you can see that there are other potential runs that would work in the coverability setting that don't originally work in the reachability setting. Some clever chappy showed the following, that unary, doesn't matter the dimension, is NL complete. And then the binary setting is a lot harder. We have p-space complete for dimension 2 onwards, and then up here we have NC2, which is a subset of P. Just worry about the P. NC2 is kind of parallel computable, and the 2 I think represent the number of processes, if you will, just to keep it kind of informal. I'm not very confident I understand this result, so I won't go into detail. Point is, it's in P, so it's nice and easy in the binary setting. It's immediately easier than the reachability one, and you can see that its depth is okay. Brilliant, that's even better. Thank you, Alex. Oh, no, it's not Alex, it's Marcel. Thank you, Marcel. And you can see that coverability in the unary setting is already a bit easier than what it is in the reachability world, because we get NP hardness at dimension 7 onwards, whereas at dimension 7 onwards in the coverability setting, we stay in NL. So we can see that in some cases, maybe coverability is as easy or as hard as reachability, but in most, if not all cases, we have coverability is kind of inherently easier. The reason I kind of chop these off with blue lines is hopefully coming later. I don't know if I'll have time, but I only care about low dimension cases, like dimension 1 and dimension 2. So yeah, I think this makes sense. Sorry for being a bit rough around the edges with some of these bounds. So Marcel said that NC2 is parallel computable, but the depth of the kind of I guess it's coming away from the talk, but let's just sort of let's say P just to keep it nice and simple. I haven't read about this for a little while, so okay, cool. I'll move on to the next board if I can find it. Again, this is kind of now really into the problems that I'm interested in. So this is kind of thanks to Dimitri for pointing this one out to me. So I will say OCN universality, and what this means is it's the one counternet universality. I'll define universality in a moment, but the OCN in particular has a unary input alphabet and binary counter updates. That's the only type of OCN I care about. That's kind of why I highlighted it earlier. So in this case, right, I have the alphabet is just the letter A for unary, and then my updates are allowed to be plus minus n. That's kind of my restriction. And now the universality doesn't have to be on the OCNs, but for this it does, I suppose. We take as input just an OCN. I've called it curly A at the top there. And then a question. So universality says, for all words, does the word belong to the language L of A, where A is kind of our automata or set or whatever. But in this case, because we have unary input alphabet, we can say instead we have all words sort of W or omega, whatever character you prefer, are equal to A to the N, right, where N is some kind of natural number. We can have A to the 0 as kind of like the empty word, if you will. We want to be able to see if we accept all of these. This problem is kind of difficult, right? Like if emptiness was already looking slightly interesting from earlier, then showing membership, which is rather than showing that the sort of the language of the one counter net is empty, showing rather a particular member belongs to the language of the one counter net. If that seems a bit harder, then universality is kind of even harder, because you have to show, well, there aren't any counterexamples, aka there aren't any words that don't belong to our language, so that we have everything in our language. And this seems like a pretty tricky problem, and sure enough it is. We have lower bound and upper bound. So the lower bound is co-NP hardness, and this is inherited directly from NFA universality. I won't go into why this is co-NP hard, but I'll go into why it's inherited. So an NFA is just a one counter net, but every update is plus 0, right? Because instead of having updates, you just read letters. That's suddenly an NFA, and the N rather than D in NFA, because we're allowed epsilon transitions, right? Because these OCNs, though not written explicitly, are non-deterministic. And it turns out that NFA universality is currently hard. So you can just kind of reduce, which is nice. But the reason why NFA universality is currently hard is tricky. It's not particularly wild. There's a pretty old paper that goes over it. It's a nice result. I think the proof is pretty cool, but I think it kind of comes away from this presentation, so I won't touch on it too much. And then the upper bound, this is kind of more recent. I want to say the date is 2020 on this upper bound, maybe 2019, so it's like super fresh. The upper bound is co-NP to the NP. And the reason why is kind of cool. So co-NP to the NP means the problem is co-NP in co-NP with access to an NP oracle. So let's think about non-universality, right? Let's get rid of the co and look at non-universality. So non-universality would be finding a word W in the form A to the N that doesn't belong to the language L. So if we're in co-NP, we can say, well, maybe we can try and guess this word, pull it out of thin air, and then use an NP algorithm and then call upon the oracle for that NP algorithm to show that it's not in there. So this is kind of like the non-membership problem. And this is kind of the same as membership in a way. But we don't know N, right? N could be like really big. Like this one counternet may accept all A to the N up to N a million, right? So that means it accepts all words with a million or fewer A's, and maybe it accepts everything with a billion or more A's. So kind of counterexamples are like massive in size. So the only way we can write this down in a meaningful way, because writing down a million A's like this kind of gets boring and tedious after a while, is writing it in the form A to the N, but encoding the N into binary. So kind of compressing N and then writing it as the form A to the N. And that's kind of what compressed membership is. It's membership, but we kind of like squeeze our word rather than writing it out in full. Hopefully you can see why this is a sort of slightly trickier problem. And I've written down here, N may be kind of exponentially large, so we need to write it in binary, not unary. And it turns out that this problem of compressed membership for one counternets is in NP, and therefore you can use it for certificate checking for co-NP with the NP oracle for universality. The next slide should hopefully talk about why this is NP. This is kind of recent, and I'm finding it interesting. But kind of importantly, this problem has an unknown complexity. It's not NP complete. It's, I think, NL hard, and in NP, that's its gap. I'm hoping to find NP completeness, or maybe show it's in P, squeeze the gap a bit more. I'm not sure. There's something interesting here, to say the least. This is kind of exciting to me. I'll come a bit more as to why. But before I move on, a little sad side note. I think it's one of the first things I tried to do over the summer before the PhD started was like maybe get a cheap result for free. So Dimitri showed semi-linear set universality is co-NP to the NP complete. So we have both co-NP to the NP membership, like here, and hardness. And the hardness is key. So just to be clear with what semi-linear set universality is, I'll write over the top of this blue and red, hopefully it'll be clear. You take as input a semi-linear set in the form that we showed earlier. And we want to say, okay, is this thing equal to the naturals? This is dimension 1. You could have a multi-dimensional semi-linear set. That stuff gets kind of crazy difficult. So we'll just stick with the one-dimensional case. And it's been shown to be co-NP to the NP complete, which seems relevant, right? Like I then tried, can I find a one counternet with language exactly equal to the semi-linear set S as input? So we have a reduction where we take an arbitrary instance to this problem, semi-linear set universality. I then convert conveniently in a short amount of time to some nice one counternet. And that one counternet has exactly the same language as the semi-linear set. And then if we have S is universal, we then get that the language of the automata is universal. And then that would get our co-NP to the NP hardness, and then kind of improve this bound, and then we would get completeness here. That was kind of the dream, right? The goal. This failed very nearly. I don't think I've got times to show the failure, but it's certainly interesting and showed that the result wasn't as cheap or as easy as I thought it would be. Much to kind of my disappointment, but it certainly showed that there is something going on, right? Like this gap is closable potentially, and the reason is going to be non-trivial. I've spent too long thinking about it. Maybe I've like looked past obvious things that will help me, but I hope this is kind of introduced where the gap comes from. But yeah, I think it's probably best to understand NP membership for compressed membership for OCNs. Slide 6. Before I go any further, are there any questions regarding one counternets or universality or semi-linear sets or anything I've talked about?
I'll just comment that I also can't find anything wrong with your logic, and I think it is just a harder problem than than it might initially have appeared. So yeah.
Okay. Yeah, I guess I'll just add a footnote. I've recently spoken with Alex on this, So I see Alex as maybe my equivalent of an NP oracle, right? And I hoped to I hope to kind of explain this to him and sort of work together. But I showed him my near proof, and it's unfortunate. It doesn't appear that you can design a one counternet easily that accepts a semi-linear set as its language just on command. You can do it, but I don't think you can do it in a small amount of space. You could make a ridiculously large one counternet that would do it for you, but I don't want ridiculously large. I want like polynomial conversion between the two, or maybe even linear, something better. So yeah, this problem is kind of tricky, but it immediately appears harder than CoNP hard itself, if that makes any sense, because this machine is just a lot stronger than an NFA because it has a counter, and that counter has the non-negativity constraint. So this thing is already more powerful. So it feels like is it in the middle? And another note, if you have a problem that is co-NP to the NP complete, it must be the case. This is just a little thing. This implies that the problem belongs to NP, and it's NP hard. I didn't mean it belongs to NP. It's NP hard, and co-NP hard. Now we get this for free. We've got it here. So if this thing is co-NP to the NP hard and therefore co-NP to the NP complete, we need NP hardness. And I've tried to look for NP hardness and I can't see it obviously anywhere. So there's something kind of spooky going on. That's kind of part of the fun, right? Okay, so slide 6. I don't see any other questions. There it is. OCN compressed membership, a bit more on it. So to find the problem a little bit more formally, again, I'll have my OCNs be non-deterministic ones with unary input alphabet binary counter updates. And the input is now we take two things. We take the one counternet just as before, and we take an integer n. And this is specifically written in binary, and that's kind of the key here. Then the question, does A to the n belong to L? That's literally it. Now this has an open complexity gap. It's NL hard. I won't focus on the lower bound for now because I don't think it's that interesting. Maybe it's P hard as well, which means it's like it must be like at least polynomial time. I'm not sure here. This is partly written on these slides that when I look back on them, I remind myself to find this out. But it is at least NL hard. I think this can be shown by just regular, if you forget the compressed membership. I think that thing is already NL hard, so adding compressions just makes it worse. So let's look at the upper bound. So I've stole this from the paper that I've been reading about the universality of these machines. And the way they showed this result co-NP to the NP membership was you guess, so in the co-NP setting, you guess a counterexample to universality. Then you take that counterexample and you verify it using an NP oracle. But you need to verify it. You need to make sure that the problem itself of verifying non-membership is actually an NP. So we kind of ask why, and this is saying like, why is this thing an NP? That's the question here. So I'll try and pen it live because most of this hasn't been live. If A to the n belongs to the language of the automata, that implies there exists a run R that takes you from the initial state, we'll call it S0 starting state with counter value 0. That's the starting configuration for all OCNs. And it runs along R and it takes you to the final state, let's call it T, actually T for final state because it's after S, and some kind of counter value, right? We don't care the counter value. The counter value is not important. Point is it will be greater than 0 or greater than or equal to 0 because of the non-negativity constraints. You can kind of bracket it off the side. Now, this run might be really, really long, like really long. This could be like exponential, maybe even like worse. The idea being like, just as a sort of thought, there are moments that might look like this in the machine. So if n is huge, right, because it's encoded into some compressed way, n could be like massive. We could have a transition that reads in an A and just adds 1. Let's say we got there on an epsilon plus 0 and we left on an epsilon plus 0. Sorry, we didn't leave an epsilon plus 0. So we entered with an epsilon plus 0. We could like read A's for a while and add 1 to our counter value. But then suppose we had like a minus 1,000 coming out. And it didn't read anything, so it's an epsilon minus 1,000 transition. That means we have to take this loop well, at least 1,000 times, right? If we can afford to take this this transition out to other parts of the counternet. That's assuming that we came in with 0 counter value. So assuming you came in with 0 counter value, you have to take this 1,000 times to be able to leave. So when you write down this run, if you were to write it down in terms of states, if I called this state, let's say we had a state over here, let's call it A, let's call this state B. Maybe A is a bad choice because that's the letter. Let's call this X, Y, and Z. These are the state labels. The run would be something, and then X, and then Y's forever, basically, or at least 1,000 of them, and then a Z, and then some other nonsense. And this is big. Like, this is not okay. The reason it's not okay is these updates are written in binary, hence binary counter updates. And so the representation of this 1,000 value is actually log of 1,000, which is significantly less than 1,000 as it turns out. And so we can't really afford to write down runs that are really long. They're just, they're outside. This would be a exponential sized certificate for this problem. So then, okay, if we wanted to write down the run as our certificate to prove that, yeah, A to the N does actually belong to the language and hence get membership, we kind of need a better way of writing down runs. Now, I'm not going to show you exactly the mechanism of doing this, but there's a kind of standard form where it's sort of not standard. Let's call it linear form. It's really nice. The idea is that you can take a path tau naught to a cycle, and then take another path to another cycle, then take another path, etc., to another cycle, etc., to the final cycle, and then the final path. And this starts at S and this ends at T. And the number of paths and cycles here, K, is small. It's kind of like roughly the number of states squared. So it's like polynomials, not very many paths and cycles. And the size of each of these is roughly, so the size being the number of states in each path or the number of states of each cycle, is at most the size of Q. So in total, this thing is like already bounded above by like Q cubed, which is polynomial. It's not kind of exponential in the size of the encodings. Let me just turn on my light. And there are kind of maybe some exponents here. Let's call it E1, E2. Maybe you take cycles multiple times. But we're allowed to write these, we'll call them like exponents of the cycle, the number of times you take a cycle. We're allowed to write these in binary. Like, that's okay. And someone else who was quite clever came along and showed, well, if I have a run like above, this implies the existence of a linear form run. And so if you have membership, you have a run that shows that you reach the final state, therefore have membership. This also implies the existence of a linear form run, and I'll scroll down a moment. Now, if this implies the existence of a linear form run, we have something we can now kind of guess because it's polynomial size. So the NP kind of algorithm, if you will, is guess the linear form run like equivalent, so run equiv of R, and then check it. And I'm going to put a big asterisk here. So, okay, sure, this thing is polynomial size because it's like Q cubed long, and the exponents that you tack on at the end are at most the size, like they're roughly linear in N, where N is this value here, the input kind of for the compressed membership. So this thing is linear in the size of the input of the problem, right? Because Q is the number of states, N is this thing, and it's linear in the size of N. So because the size of this, you encode both of them in binary. So, okay, if you're happy with this being a polynomial size, then you can guess it, right? That's legal in NP. Now we need to check it. Turns out checking it you can do in I think, less than quadratic time. So the idea is you have some run tau to some cycle gamma 1 to some other run tau 1 to some other cycle number 2, etc. You get the idea. And then the final cycle and the final run. They look like J's, not taus. I hope it's okay. You basically, to check this thing, is you go along this and you check the non-negativity constraint. Then when you get to the cycle, you do the same thing. You check non-negativity constraint on the cycle just for one iteration. Then you store the update, we'll call it U1 for the update of the cycle. Then you multiply it by the number of times you update, and then add that onto the counter. And then you repeat. So you keep this counter value here, you check non-negativity as you're going along. You non-negativity once on the cycle, you get U2 to work out the whole update of the whole cycle. You multiply that by the number of times you would do the whole cycle, add it onto the counter, etc. And you go through. And at most you're spending like roughly linear time on each part. So it's probably a linear algorithm overall. And then once you get to the end, you kind of give a smiley face. You're happy that this run is executable, which means that you don't violate the non-negativity constraint, and indeed that your guess was correct in that the actual run corresponded to the right number of like A's read along the path. You need to check those as well. So you might have a second variable that says like, okay, I'm just checking I read the right number of A's, and you check this in linear time and you're done, right? So now I think everyone's happy. NP is you're allowed to sort of non-deterministically guess something in polynomial time and then check it in polynomial time. And that's what we're doing. You could imagine this slightly differently as you non-deterministically guessed the path as you were going. It's the same kind of thing in disguise, but I think this gives a bit more of a clear understanding. The intelligent step is really this implication, like how they managed to get a polynomial sized run for any arbitrary run for an accepting run of A to the n is pretty cool. It's neat. It's not ridiculously complicated. It uses a fairly nice technique that I think is explainable. I don't have time, but this hopefully now convinces you the upper bound is NP. And this is what I've been working on, and I'm stuck. That's kind of part of the fun of doing a PhD, right? So I'm happy with NP, happy with NL hard. I think it's significantly harder than NL hard, just as an intuition. Is it NP? Like, is it somewhere in the middle? I don't know. Is it NP complete? I don't think so. It feels slightly easier than NP completeness. At the moment, I'm kind of spending a while looking for interesting counternets that have kind of cool gadgets in them. They maybe accept weird sets of words. Maybe like forget universality for a minute, just looking at interesting counternets for which the compressed membership is therefore tough. Like if I have an odd language for an interesting one counternet, then it kind of feels like compressed membership is therefore quite tricky. So maybe a good way of attacking this is finding interesting counternets to kind of affirm that this problem is tough, in that maybe it's NP hard. I don't know, and I haven't found anything particularly like really cool. And in particular, I've not found anything that these can do that polynomially sized NFAs can't do. And I think that's kind of where my journey has brought me to, is I'm really trying to like work out what makes one counternets with unary input alphabet binary counter updates tougher and like stronger than NFAs. And yeah, these are the problems that excite me. If anyone knows anything obvious about what I've said, I'd love to hear it. Or maybe just an insight. Maybe you've thought about this problem or similar problems before in a completely different way. I'm very happy to hear it. I've thought about these problems in various ways. I wanted to show one more thing, but I really am at the end of the meeting. I would be pushing it a bit much. But I think this is kind of a nice summary. So yeah, any questions? And I'll stop the recording now.